Okay. So thank you. Welcome to my talk about accelerating pattern matching queries in hybrid CPU-FPGA architectures. This work was done together with Scholt, who sits over there, Mushin, which is a postdoc in our group, and our advisor, Gustavo Alonso. So there is an increasing amount of user-generated data. For instance, user tweet, they comment on different type of things, and they write product reviews. And most of this data is text data, and it's also partially stored in relational databases. However, relational databases are not performing very well when it comes to complex string operations or text analytics, and we can illustrate this on a simple example. So here we look at Monet DB and a commercial row store, which we call DBX, and we have two queries. The first query is a like query, where we do substring matching on three substrings. And in the first query, we use a regular expression operator, and we actually do the same substring matching on the same three substrings. So the result of this query is going to be the same. However, by just going from the simple operator to the regular expression operator, we see that the response time increases by a factor of 20x. So relational databases are really not suitable for complex text queries. And one way to address this is by the use of accelerators. And there's actually existing work using GPUs or Xeon+/s to accelerate string matching. And in fact, they report the high speed up over CPU-based implementations. However, they have to make some assumptions. And one of them, for instance, is that the data is already local to the accelerator, so it's stored on the accelerator. Or once they actually would consider the data movement between CPU and the accelerator, the benefit of the acceleration is heavily reduced. Some approaches also requires that the data layout is adapted to the execution model of the accelerator, or with increased complexity of the patterns, we see like generally a reduction in performance. But more importantly, generally it's often not clear how would we actually integrate such an accelerator into an existing database engine. And the reason for this is that when you introduce the accelerator into the database, you either have to partition your data between the CPU and the accelerator, or you have to move it back and forward. And this really introduces an overhead which hinders like the widespread adoption of database accelerators. However, there is now new hybrid architectures emerging. For instance, we have from IBM the Power 8 system, which comes with copy, where the accelerator gets cache coherent access over PCI Express. Or on the other side, we have from Intel the Xeon+FPGA platform, where the FPGA is connected over QPI and can access direct memory. In both these architectures, now the accelerator has cache coherent access to the main memory, and thereby we remove the need to move data back and forth or partition it, since we have this direct access. And in this work, we're going to use the Intel Xeon+FPGA prototype platform, in particular version 1. And this is a machine which has two sockets, and in one socket we have a Xeon, Intel Xeon with 10 cores, and in the other socket there is an Altera Stratix 5 FPGA. And these two sockets are connected over QPI, and main memory is we can only install main memory on the socket of the CPU. And that means that the FPGA has to always go through QPI if it wants to access the memory. And for read-heavy workload, we measured around 6.5 gigabytes read bandwidth, and if we have a mixed workload, 50% reads, 50% writes, we get around 3 gigabytes in each direction. But here I also want to mention that there's actually already a new version out, the HARP version 2, and there we actually, some of these limitations are already addressed. So you will get higher bandwidth from the FPGA. There are two more PCI lanes between the Xeon and the FPGA. The FPGA is newer and correspondingly larger. And very importantly, now this is all in one socket, so there's not one socket occupied by the FPGA. So although FPGAs are becoming more popular, I still want to give you a high-level overview of how they actually work. So as the name says, there are field programmable gate arrays, which means we can program them with an arbitrary circuit. And once they're programmed, they act similar to an integrated circuit. However, they run usually at a much lower frequency, somewhere in the range to 100 to 400 megahertz. And internally, they consist of an array of configurable logic blocks, the orange blocks here. And this array is also interleaved with on-chip memory, which is called block RAM. And these are the green blocks here. And to connect either the logic blocks with each other or the logic blocks to the on-chip memory, there is a configurable routing network. And when the FPGA is programmed, this routing network together with the logic blocks are all configured. So let's go to our regular expression engine, or more importantly, how we actually make it parameterizable in hardware. So there's already a lot of existing work using FPGAs for pattern matching in the domain of network intrusion detection or also complex event detection. And FPGAs can do this very efficiently, and the reason is because you can map these patterns to a non-deterministic finite automata, and this NFA you can directly implement in hardware, like you lay it out as a circuit. And in an NFA, since it's non-deterministic, we can have multiple states concurrently active, and if it's done in hardware, this is really truly concurrently, so multiple states can be active. However, in software, generally regular expressions are implemented as DFAs, and there only one state is active at a time. And to illustrate this, we have an example expression here, AB plus or BA plus followed by C, and the corresponding automata. So on the left side, we have the NFA, which is very compact, and on the right side we have the DFA. In this case, the DFA is one state more, but it has also many more transitions. Since only one state can be active, this is necessary. And if we get more complex expressions or large expressions, the DFA will actually grow much quicker in comparison to the NFA. And the larger the DFA is, the more resources it requires. So to illustrate how they actually operate, we have some example input here. So first we consume a character A, and this will activate state S1 in both of them. And then we consume a character D, and that is actually not part of our expression. So again, only S1 is active. And then the third character is again A, so we see S1 is active again. And now the fourth character is a B, which in the DFA, we will just activate state S3, while in the NFA now we actually have two states active at the same time. So S1 activated itself and also activated S3. And then there's more character Bs in the stream. And then finally we have a character C, which in both automatas will trigger the final state. And once we reach the final state, we know that we had a match in our regular for this expression in the input. So this was a very short expression, and therefore the NFA was quite compact. However, we said in the beginning we want to look at user-generated data, and there we look at larger expressions and more text. So let's look at an expression which is more natural language. So we have SIGMOD wildcard Chicago or relay, and if we map this to the NFA looks like this, and now we have many more states. And if we map this to the FPGA, each state requires actual hardware resources. And the larger the NFA, which means the more complex expression or the longer the expression, the more of these hardware resources we require. And as you have seen, we actually have to connect them through this routing network. And it might be possible that at some point the NFA becomes so large that we're not able to connect it and still meeting some frequency. So if you want to run it as 200 megahertz, there's some limit at which, at that point, we are not able to run it at 200 megahertz. And we address this by compressing the NFA. And since we have kind of many states with only one transition and only one state it can reach, we can actually extract these sequences which we have from the natural language. So we extract SIGMOD, Chicago, and relay, and now we can compress our NFA to only 3 states. However, now in this NFA, the transitions are not triggered by a single character, but by the sequence of characters. And to address this, we use something called a character encoder, and thereby we can decouple the state transition from the character matching. And this is something that was used before, but in a different purpose. Essentially, before it was used to save the number of matchers. For instance, if you have multiple times the character A, we would only have one matcher, which would then trigger multiple states which want to observe this character. However, we use it to build sequences of characters. So if we look at our character encoder internally, we have these different characters loaded in, and now we can actually chain them together into a sequence, and only the last character in the sequence, here that's D, will then trigger a state S0. We are also able to configure them differently such that two of these matchers actually build a range together where one of them is checking for the lower value and the other one for the upper value. And then if the incoming character is between these two values, they will trigger a state. We also have a flag to support case insensitivity, so we can check at the same time the lower and the uppercase character, and if one of them matches, it will trigger a state. And this can be extended for collations where we would match the same alternations of a character in concurrent, and then if one of them triggers, it will correspondingly trigger the state. And if you look at this architecture, we actually see it would be very easily to switch out these characters and just match a different string instead of SIGMOD. And thereby we are actually able to parameterize this hardware at runtime by just swapping out the characters with different characters. And also these flags are just individual bits. And that's exactly what we are doing. But this is only for the character encoder. So if we look at the whole, how are we going to parameterize the whole NFA? So essentially we build like a generic NFA here in the middle, and this example is only for states, and these states are fully connected. And the connections can be enabled and disabled at runtime. And to illustrate how we parameterize this generic NFA with these 4 states and the character coder on top, we look at the regular expression here, A or B wildcard C. In general, this would lead to this NFA, but now we have our generic NFA, which we want to parameterize. So first, we extract the characters A, B, and C, and we can load them into this character encoder. And second, we need to know which character triggers which state. So for instance, A and B both will trigger state S1. So in this trigger matrix here, we enable these edges, or these trigger edges in the NFA. And then thirdly, we have the state transitions, which are encoded in the state transition matrix, and we can enable these 2 state transitions. So once we have these 2 matrices, the trigger and the state transition, and also the characters, we can actually just take these parameters and store them in a configuration vector. And this can be done in a very compact format. So for us, this only requires 2 cache lines, so 2 times 512 bits. And then these 2 cache lines we can send to the FPGA such that the regular expressions engine in hardware can parameterize it themselves. And since it's only 2 cache lines, this will only take 2 cycles on the FPGA. So as you might know, the NFAs are only consuming 1 character at a time, or 1 character per cycle. And to get high bandwidth, we actually deploy multiple of them in the regular expression engine, so up to 16s. And we introduced a string router module in the front, which takes the strings coming from main memory and distributes them in round robin to the different NFAs. And then on the other side, we have a module that merges these results in the same order. So the result is either match or non-match, and if you have a match, we also have the position of the match. And then these results get written back to main memory. So with that, I would like to go to the integration into the database. So we integrated this into Monet DB, a column store. And one advantage of the column store is that since we parse the data actually on the FPGA, it's easier to parse the column store, and therefore we need less logic on the FPGA, and we can save some hardware resources. And the layout for strings is we have a string heap with all the strings and some metadata, and we have a column with offsets pointing into that string heap, and this structure is then parsed by the FPGA. Another advantage of using Monet DB is that in Monet DB, HUDF can operate on a complete column, and thereby we can offload the complete column to the FPGA, and we don't have this overhead of calling the FPGA for each tuple. And this reduces the overhead significantly. So let's zoom a little bit out and go back to the whole system. So again, we have the CPU and the FPGA, and they can communicate with each other through shared memory, which is the green box on top. And we have 3 main components in our system. First, we have Monet DB, which we extended with this hardware user-defined function. Then we use Centaur, which is a framework that bridges the gap between software and hardware, and essentially provides us a nice interface to create and monitor the jobs on the FPGA. And then on the FPGAs, we are able to deploy up to 4 of these regular expression engines. And each of them can actually process data at 6.4 gigabytes per second, which will already be enough to saturate the QPI bandwidth. So to tell you how these actually interact, these components, we go through a quick walkthrough. So first, let's say a query enters the system, and this query contains a regular expression. So we will call into the UDF, and then the UDF does this configuration vector for the regular expressions and stores this vector actually in shared memory as parameters. Then it will enqueue a job into a job queue also in shared memory, and this job queue is observed by a module on the FPGA, which is called job distributor. So it dequeues that job and assigns it to one of the engines. The engine will then go and fetch its parameters from memory and configure itself with that regular expression and then start the execution. Once the execution terminated, it will update its status also in shared memory, and this can then on the other hand be observed by the user-defined function, which will return the result column back to Monet DB. So with that, I would like to go to the evaluation. So in the evaluation, we looked at 4 queries. And query 1 just does a simple substituting using the like operator, while query 2 to 4 actually do regular expressions, and which are more compute intense. All of these queries cannot benefit from an index and require that we scan over the whole data. So first we wanted to look into the overhead of offloading this or going to the FPGA. And for this, we on purpose took a very small data set of only 10,000 tuples. So you can actually see the overhead more clearly. You see the orange bar and the gray bar at the bottom. These are actually actual processing of the data. And then in the middle, we have the overhead. So red is for creating the FPGA job. Blue, which is not visible because it's only a few microseconds, is generating this configuration vector, which I explained before. And then for brown is the time we spend in the user-defined function on the software side. And this overhead is actually fixed. So when we increase the dataset size, this will stay fixed, and only the processing will proportionally increase with larger data. So while it looks large here, this will get very small if we have larger and larger datasets.
This was the same regular expression that we tried with Monet DB and like vanilla without your FPGA? Initially, you had like a slide with the results of Monet DB doing your
these are these 4. Okay. So, and as you can see here, actually all 4 queries have the same response time. And this is because the NFA implementation actually can perform the same independent of complexity, because we just consume the data and the NFA evaluates it. So let's go next to evaluation of the throughput. So first we see on the left we have Monet DB against Monet DB extended with our FPGA-based operators, and we can see that for the simple substring query, actually Monet DB performs better, and this is because the FPGA is actually memory bound, while Monet DB or the CPU has a higher memory bandwidth, and here it can benefit for query 1, which is not compute intense. But as soon as we increase the complexity, the problem is no longer memory bound, and the performance on Monet DB actually starts to drop, and it's around 1 order of magnitude lower than what we have for the FPGA. On the other side, we again have this commercial row store, and in that row store, one client, only one thread is used per client, and therefore the performance increases with the number of clients. And we see that only for the simplest query, actually, this database is able to match the performance of the FPGA. And maybe you wonder why we actually compare against 10 clients here. So as you have seen in version 1 of this platform, the FPGA uses a complete socket. So we really wanted to make the socket versus socket comparison. So we have the FPGA in one socket, and in the other socket we have this Xeon CPU with 10 cores. And that's why we have this comparison. And you already see that we are like in the same ball. I mean, for simple queries we are slightly slower, but for complex queries we can easily beat the CPUs. And then in the next generation, we actually will have this all in one socket, and you don't have to use one socket just for the FPGA. As we integrated this FPGA-based operator as a hardware user-defined function into Monet DB, you can actually use it in any type of queries. And there's only a few queries in TPCH which use the like operator. One is query 13. And here we just switched out the like operator with our hardware operator, and you see the comparison between Monet DB and Monet DB with the FPGA, and we measured like the response time of a single query, and you see that we get about half the response time using the FPGA-based operator. But now let's say we want to actually increase the complexity by, for instance, instead of using the like operator, we use the I-like operator, which is case insensitive. Then on the software side, we see how the response time roughly doubles, while for the hardware, we get like exactly the same response time. So finally, I want to go back to the accelerators we had in the beginning. So we saw that you can actually do regular expression evaluation on GPUs, but also on Xeon+, and we presented how we do it on FPGAs. And on FPGAs, this is actually, the performance is independent of the complexity, while for GPUs and Xeon+, usually the DFA is used, and the larger the DFA grows, this will have an impact on the performance. However, if you look at the throughput, so first we look at the throughput if the data is local, we see that if you use a GPU, you might get around 60 to 70 gigabytes in the first approach, which only does string matching, or 10 to 15 in the second approach. And if in the Xeon+, you get even more, you get 30 to 40 gigabytes for doing regular expression. And our approach can do 25.6 gigabytes if we neglect the memory bandwidth limitation. And there's no numbers, only for the second GPU work, we get the numbers including the PCI transfer, so there we see that it goes down by an order of magnitude. And in our case, we're not really on the PCI, so we have this 6.4 in this work. But this is not really a comparison among accelerators. So GPUs clearly benefit from their fast GDDR memory, but what we want to show in this work, this is actually the FPGA is no longer an accelerator and becomes a specialized core. It is very close to the CPU, and therefore we have this direct memory access, and we don't need to move data back and forth. And actually looking at the next iteration of Xeon+FPGA, we see that this bandwidth will increase, so we should get like 20 gigabytes per second, and the FPGAs also become larger and we have much more tighter integration. And we actually believe that in 2 years or so, you might be able to buy this Xeon CPU and you will have an FPGA in there. And one way to use it is doing this regular expression evaluation, and you don't need an external device like a GPU. Of course, you can still do that, but the FPGA will be there anyway, so you might just use it for this type of workload. And that's kind of my conclusion. We will have a demo tomorrow where you can see this operator, but also 2 other operators, and they're all integrated together into one database, and we can run multiple hardware operators concurrently. And you just have to come and look. It's really interesting. Thanks. If we had a workload where the pattern changed, so in our evaluation, the pattern was like was fixed for a specific run, but we reconfigure these regular expansions for each query every time. So we every time generate this configuration vector, and every time it's sent to the FPGA, it configures itself, and then we run the query. So we could easily swap out this configuration vector.
If you had a per row of that vector, what would the overhead be?
I didn't understand your question.
Per row regular expression. For instance, the pattern could be a function of any column. It could be different for every row.
It will be different for every row. Oh. So that means essentially the input is another row. The expression is stored in another row. Yeah, then we have to kind of change our layout a little bit, because you would need to read this. Essentially, we would read that row first, generate all these configurations, and then load them somehow at the same time as we read the data. That's a little more involved. Yeah.
So I wanted to ask about size limitations in terms of regular expression size. So you did mention that you use compression, but how soon do you need to, I mean, at what size do you need to start to compress? And also with compression, how large or can given the, how large do you get before your system kind of fills the FPGA and can't increase further, can't scale further?
Yeah. So first, we always try to compress, because actually increasing the character encoder is easier than increasing the NFA. And secondly, we did some experiments in the paper where, so currently the NFAs run at 400 megahertz, and then we try to explore the space, how many characters we can support until we have to essentially go to the next lower clock, which on this platform is 200 megahertz. So you do have this trade-off. If you see like you need much more states or characters, at some point you can reduce the frequency and thereby half the throughput, but you then get more freedom for more complexity. So there is this trade-off which we explored in the paper, and we have a graph for this. Yeah. But yeah, this is a trade-off in hardware.
Yeah. Okay, let's thank our speaker again. So